Hey guys, still here on Hurricane Day. Same shop, same doggies, same doggies. They're kind of like hanging out. They're kind of mad they can't be out with all the chaos. Okay, so in this lecture, we're going to be talking about reaction mechanisms and factors that are going to affect the reactions themselves. So we're going to be talking a lot about kinetics, but in addition to that, kind of like kinetics of a bunch of different stuff inside of the reaction that's occurring. So it's a lot of different steps. A little bit complicated, but necessary. I learned about this stuff pretty much within my first year of college in chemistry. So, just starting, most reactions do not happen in one step. Funny enough, most don't at all. It's very rare that you will see a reaction that just kind of happens all by itself in one step. So basically, everything's going to occur in two or more elementary steps is what they call it. Elementary meaning just like easy, basic. So your first reaction, 2NO yielding N2O2. And your second reaction, the N2O2 plus oxygen is going to yield your 2NO2, and that's going to give you your full reaction. So it's a series of steps that sum up to get your overall reaction. And within that reaction, you're going to have a reaction intermediate. I just crossed that out. Reaction intermediate. The reaction intermediate is a substance that is produced and then consumed during the overall reaction. So N2O2 is produced and then is completely used to where we cross it out and it doesn't even happen in this main reaction. So we call it a reaction intermediate. So when we're determining a rate law, the rate law for an overall reaction can only be found experimentally, unfortunately. So looking at this overall reaction, NO2 plus CO yields NO plus CO2. Our rate law is this right here. Rate equals K times NO2 squared. My dog opened the door and left. NO2 to the second and CO to that 0 power, which gives you just this, because CO to that 0 power just makes it 1. So then we're just left with the K times the concentration of NO2, and it's a second order reaction. So the overall reaction, we're able to kind of write that down, but rate laws for elementary steps are actually predictable. So for this step 1 of that reaction, the rate is actually, we call it K1 because it's that first step, times the concentration of that NO2 squared. We're actually able to put that 2 there. And this is the same rate law as the overall reaction, which you'll see why in a second. For step 2, this equation with this rate. Now, something really cool is for any elementary step, this is true. We put the compound in our concentration, and the exponent is actually the coefficient for that compound. So if you look up here, that 2 comes from this 2. And the 1s right here that occur are from the 1s that are in front of these compounds. So it's pretty cool. And that is, you can do that for any elementary step. So NO3 is consumed as soon as it is produced. So this is your intermediate compound, or intermediate, I forgot what they called it. Intermediate. Adding CO does not increase the rate, and because of that, it makes it a 0 order, because CO doesn't really do anything. It's just there. The rate of the overall reaction is always equal to the rate of the slowest elementary step. So think of it like this. If you and your friend are running a race, but it's like a team race to where you both have to finish in order to like place, if your friend is slower, you have to either run with your friend or you're going to be in a lower place even though you finished like first. So if this is your slow reaction, then the overall rate of the reaction follows this rate law because that's the slowest one. All right, so to you, that was like a second delay. To me, that was like an hour delay. A child came in here, and children. So, continuing on, I don't even remember what I was talking about, where I was. Yeah. The overall reaction is always equal to the rate of the slowest elementary step. So, I'm sure I talked about it in length, but since this is the slowest reaction, the rate is going to follow this rate law, and we basically just ignore that one because if this is the slowest one, that's what really matters, and that's what's going to drag us down. All right, so moving on. When the mechanism has a slow initial step, the rate law for the overall reaction is equal to the rate law for the first step. So because this is the slowest one and it's first, we're going to follow this step because that's our buddy slowing us down. This reaction proceeds at the rate of the slow step, but the problem is that NO3 is an intermediate, so its concentration is unknown. To solve this problem, we must modify the rate law. So because this is the slow step, we can use this rate law. However, we don't know the concentration of this NO3 because it's the intermediate. We can't tell what's happening to this intermediate because all we see is this and that. So we have to modify the rate law. So what we do is we take the rate laws from both sides and we kind of combine it to get this concentration of NO3 on one side. And then we can use that concentration of NO3 and put that into our slow reaction. So overall our rate law looks like this. Because we've got to put this equation in for NO3 that goes in right here, and then we have everything else going with it. So it's kind of a really long process in order to do that. But overall, we end up getting this. Everything kind of cancels out, and we get the rate is equal to K3 times the concentration of NO squared times the concentration of O2. Is basically what that turns out to, because this K1 and this K negative 1 kind of cancel each other out. And then this NO combines with this NO, and it gets NO squared. And then you just kind of add this O2 down, and then this K2 kind of turns into a K3. All right, so moving on. Determining a rate law. So chemists determine the rate law through experimentation. It's pretty much the only way to do it. They use the rate law to figure out what the elementary steps are. So if we have like a reaction, we kind of don't really know what the elementary steps are because we don't really see it happening. So they use the rate law to figure out those elementary steps. The rate law tells them what the slowest step is, and then they try to figure out what the fastest steps are. So they kind of work backwards from what we've been doing. So here is a really large, complicated chart. Let me just kind of point it out to you. So molecularity, so it's uni, bi, ter, 1, 2, or 3, reactants, sorry. If we have one reactant, then our rate looks like this with just A by itself, and it's a first order reaction. If we have two A's in our reactants, then it's going to look like this for our rate law, and it's second order. If we have A and B in our reactants, our rate's going to look like that, and it's second order as well, because we have two reactants. If we have anything with ter, these three different things going on, then our rates are going to look like this, and those are all third order because they have three reactants in them. Ter-molecular elementary reactions are very rare because the collisions, it's almost impossible to get those collisions to happen because they must be simultaneous with all three of the particles, and there must be enough energy, and they have to be in the correct orientation. So it's like everything must happen exactly the way it's planned in order for those to occur. The value of the rate constant K is going to increase with temperature. So if temperature increases, your rate constant is going to increase, making your rate increase in general. So we have two processes here. Which process has the higher rate under standard conditions? So what I'm seeing is two bimolecular.
Stephanie, come here.
Okay. All right. I have no idea if you heard that, but that was another 20-minute delay, which happens here a lot, but that's okay. So I have no idea what I was saying, but I will continue, I guess. So we have two processes. They are both second order, I believe, because there are two reactants. Or is that first order? I'm so sorry. It's second order. I was right. Okay. So we have two, okay, life right now. Okay. We have two second order reactions with rate constants. And it's asking us which process has the higher rate. So honestly, it'll just be the one with the higher rate constant because they're both bimolecular second order processes. So it's going to be this first one with the higher rate. So process 1 proceeds at a faster rate. Both of them are second order, and both of them have reactants with 1 molar concentrations. The rate constant for process 1 has a larger magnitude, which means it'll have the higher rate. But looking at this one, we've got two different rate laws here. So it's asking us which one has the higher rate. Process 2 is actually more likely to proceed at a higher rate because of the slow step in process 1 requires a simultaneous collision of 3 particles with sufficient. Basically, this one is the TER, or it has 3 different reactants, and this one only has 2, which makes that one the faster one because this first one has 3 different things, and they have to collide all at the right time, all at the right speed, all at the right energy, all at the right way, which makes it a lot harder and a lot slower. So it's that second one that's actually going to be faster, only because it is a bimolecular. So factors affecting reaction rate. Number 1, the rate of collisions between the reactants affects the reaction rate, so how fast are collisions happening. The percentage of collisions with an orientation that could produce a reaction, so are the collisions happening to where an actual reaction is happening, or are they just kind of bumping off each other because the way they're colliding isn't making a reaction. And number 3, the percentage of collisions possessing sufficient energy. So is there enough energy in this reaction? Are they pushing against each other with enough energy to actually react, or are they just walking into each other like at the mall? So collision rates increase as the concentration of the reactants increases, as well as the temperature. So think of like when we had a gas, and we had like all these little molecules, and if we added more collisions are going to happen, and the pressure increased. So if we add more, there's going to be more collisions, and then if we increase our temperature, they're going to be moving a lot faster, and then there will be more collisions happening because they're just moving so much faster. Not every collision is going to trigger a chemical reaction. So look at this. We have different molecules, 2 different molecules that can collide, and if they collide with the right orientation, they will yield a reaction. So basically, when these 2 come together, these 2 right here, when they come together, there's not a reaction happening. It's not perfect. It has to be perfect for there to be a reaction. So when these come together, we can actually get these products occurring. And so a reaction will actually occur because of a perfect alignment. All right, so now we're going to talk about activation energy in these reactants. So basically, the biggest thing to pay attention to is this is potential energy. Potential energy on the y-axis and reaction progress on the right axis, so basically time. So the kinetic energy from colliding reactants is converted into potential energy in bonds. So the kinetic energy of all this stuff colliding makes bonds, basically. And so when we have all these things combining, the potential energy increases because we're actually gaining bonds instead of just collisions. So instead of them moving all around, they're actually forming into something that is kind of stable. And then from there, they can move down, form some more bonds, and eventually you'll get your products. They disengage some bonds. So this AB bond actually disengages, and you get a single replacement reaction down here to where you have actually some collisions with A now is moving all around. So we're back to less potential energy actually down here because the A can move more freely. And that has to do with the exothermic or endothermic reaction. This one in this case is a exothermic reaction because at the end of it we have less potential energy than we did in the beginning, which means we have more kinetic energy because energy is constant. So E collision, the energy of the collisions must be greater than or equal to the energy of activation for the reaction to happen. So basically, the energy of the collisions must be strong enough to overcome this hill, basically, to run over. If the energy of the collisions is less than this energy of activation, then the reaction will not happen at all. It will go like this, and it'll just kind of teeter back down, which is what you'll see right here. It'll go up, it'll try and make the bonds happen, but then it'll fall right back down to the reactants because it's just not strong enough. There's not enough energy, there's not enough perfect collisions, there's just a lot of things going on there. Yeah, it'll just kind of slide up and down, and it'll do that forever. So reaction rates depend on the magnitude of the energy of activation. So if we have a bigger energy of activation, if we've got a bigger hill to get up, it's going to be generally slower. If we've got just a small little hill to get up and that activation energy is smaller, we're generally going to have a faster rate. Kind of intuitive. So generally, if less energy is required to get over the hump, more reactants will collide with enough energy. So if we have the smaller hill, more of these reactants are going to be able to come at each other easily, meaning there's a faster rate. So collision energy and temperature. Fraction of collisions with a given kinetic energy. So basically this graph is telling you how many of these molecules are colliding based on this speed or this speed or this speed. So like at this speed we have like 6, and at this speed we have like 8, and this speed we have like 10. That's what it's saying. So at higher temperatures, so this is at 1,000 Kelvin, this is at 500 Kelvin. At 1,000 Kelvin, we have more molecules at this speed, the most molecules at this speed. But at 500 Kelvin, we have the most molecules at this speed. So they're saying when we increase our temperature, more of our reactants will collide with enough energy to cause a reaction, meaning we'll have way more molecules over here at this really fast rate. With the activation energy over here, it'll be much easier for them to get there. Whereas only this many of the first one at 500 Kelvin are actually getting to that activation energy, whereas this many are getting there on the higher temperature. That was a lot of writing. So the activation energy for unimolecular decomposition reactions. The energy required to break the bonds in the reactant is obtained during the collision with a background or solvent particle. So basically, the energy required to break the bonds in a reactant, so breaking the bonds, is obtained during the collision with the background or solvent particle. So when the energy required to make this break apart happens because this is colliding with a bunch of stuff. So for this reason, unimolecular decomposition rates increase as temperature increases. Same thing I just said before. In summary, all three of the following conditions must be met in order for a reaction to happen. There must be a collision in general. There must be a correct orientation in that collision, and the energy of the collision must be enough to get over the hump in our diagrams. So this is a great picture to look at. This is very informative in general for chemistry entirely. So activation energy. This is our exothermic reaction. I know that kind of like goes over the picture. Bonds in the products. So these bonds have less potential energy than the bonds in the reactants, meaning they have more kinetic energy, which kind of makes sense. Exothermic, hot, that's what I think of, which you think however you're going to. Exothermic, I think hot. And that makes sense. With more kinetic energy, your temperature is kind of higher. As opposed to our endothermic reaction over here, where we have more potential energy in our bonds and our products, so they're kind of just sitting. They're not really doing anything. The delta E energy is lost, is the energy lost or gained, or, that should be or, not of, gained in a reaction. So what is the difference between our reactants and our products? Energy. Oh no. Oh no. All right, let's do this quick. Okay, so activation energy. So this is really cool also. The forward reaction is going to be different from the reverse reaction. I am going to lose internet. Oh well. Our forward reaction, so this is the same reaction, it's just flipped. So the forward reaction is this, but the reverse reaction is this. So it actually takes way more energy to do that reverse reaction than it is to do the forward reaction. Meaning, our forward reaction will happen and will fall to our products, and the products won't really be able to get right back up. They won't. The equilibrium will be product favored. Kinetic control. Thermodynamically favored processes that do not occur at measurable rates are said to be under kinetic control, meaning we can control that rate. This is often the result of high activation energies, so high hills to climb over. When a process does not proceed at a measurable rate, it cannot be assumed that it has established equilibrium. So if it does not have a measurable rate itself, we can't figure out how fast it's going, then we can't really say that it has an established equilibrium and like just balance. This is a cool picture. This is the energy profile of a two-step mechanism. So the first reaction happens, and then you've got to have enough energy to get over that second hill in order to go to the products. So those two-step reactions are actually really hard to get through because of that. The Arrhenius equation is, I'm looking at your reference table. I don't believe it's in there. It is not. And that's okay. That just means it is not expected of you on the AP exam. But we can know about it. It's okay. It's all good. I will double check if it's on your test. Remind me to double check. Because I don't want you to have to study this if it's not absolutely necessary. So K, rate constant, is equal to A constant related to the frequency of collisions and the probability of that orientation can produce a reaction. A is a constant. They will give it to you. E is... Oh, just E on the calculator. E to the negative activation energy over RT. R is this, and T is your temperature in Kelvin. This is also an Arrhenius equation. It's just with the ln, with the natural log version. Same thing. And you can use this in a graph. So you can use a graph of the natural log of the rate constant versus 1 over t to get a straight line. You'll get a linear graph. And the activation energy is actually, you can get that from the slope. So you do the slope equals negative activation energy over R, and R is just that constant 8.314, and you can easily get that activation energy using that equation. So looking at this, find the activation energy for the equation. So we use the slope. So we do rise over run. So we're going to do the change in y over the change in x. So they're picking two coordinates for us, this one and this one. Let's see if they do it for me. Yep. So change in y over change in x, they do -5 minus -1 over yada yada, and they get a slope of -1 times 10 to the 4th Kelvin. And what they do is they plug it in. The ln of k, y, equals negative EA over R times 1, blah, 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 blah. And they find that the slope is equal to negative EA over R. Plug in all their numbers, and they get an activation energy of 83,000 joules per mole, or 83 kilojoules per mole. So that's a great, that is a great thing to use in a lab, honestly. So moving on, catalysis. I love catalysts. They're just so simple, I think. So a catalyst increases the rate of a reaction by providing a mechanism with a lower activation energy. So basically it just lowers the hill that we got to climb. Catalysts are not produced or consumed in the reaction. We put them in there and they come right back out at the end, and you can reuse them every single time. In college chemistry, we used a catalyst and we had to put it right back in the jar. They are there before the reaction starts, and they are there when we are done. So the destruction of ozone, it says here, each chlorine atom will destroy about 100 ozone molecules before it reacts with something else and leaves the stratosphere. So we see chlorine plus O3, ozone, yields O2 plus ClO2, ClO. ClO plus O yields O2 plus Cl. The chlorine is back to react with another O3. So basically we started with chlorine and we ended with chlorine, and it did nothing to how much we had. And then you can just keep going and going and going. That's how our ozone is destroyed. Catalysis and activation energy. So basically with no catalyst, this is how big our activation energy is. We got to get over the hill before we can get to our products. But with a catalyst, our activation energy is much, much smaller, and we can just walk over that hill real easy. that's all the catalyst does. It just decreases that activation energy. Yeah, and it lowers it for both the forward and reverse reactions. The K equilibrium for a reaction is the same as at the same temperature with or without the catalyst. We will be doing equilibrium at a different time. Do not worry about equilibrium right now. So just skip that. Acid-base catalysis, a reactant gains or loses a proton, which causes the reaction rate to increase. Surface catalysis, a new reaction intermediate is formed, or the probability of successful collisions increases. I don't think any of this is really important, but this is more like application. Enzymes, a new reaction intermediate is formed, or the activation energy is lowered when the enzyme binds to the reactants. So, some pictures. Here is a acid-base catalysis reaction. This reaction takes place in several steps and is is very slow at room temperature, but the rate increases greatly with a small amount of strong acid is added to the system. Let's see if they have more on that. Yes, they do. Ooh, this is like college level stuff. So basically, they're showing how the electrons are moving. Changing that double bond creates a resonance. Gosh, this is like a lot more than you guys need to know. But that's okay. You are in an AP class. I guess it is important that we learn this stuff. But I did not do electron moving until organic. But you'll be there soon, I guess. So we show electrons moving with these arrows. We like go from a bond to a atom, and we move the electrons. And if we move the electrons onto here, they have to come off that carbon because we can't have a Texas carbon. Texas carbon is like a carbon with 5 bonds. It's not possible, ever. Step 2, the slow rate determining step is now faster due to a slightly positive carbon. So with the carbon positive, they want to get rid of that. They want to change that entirely, and they move the electrons down, and the H2O connects to that carbon. Surface catalysis is when reactants are in the gas phase. Catalysis is a solid. And the reactants go into the surface. The bonds within each gas molecule break, so they break apart, and they're in the surface, and the bonds form between the metal and the individual atoms. The atoms then move around on the surface of the metal because metals allow electrons to move pretty easily. The nitrogen then forms bonds with the hydrogens, and then the products just go back up into the atmosphere. So that surface kind of gives them the ability to move around and do that kind of moving and bond breaking and coming back apart. So the proteins in food must be broken down into their constituent amino acids, which are used to build new proteins in the cells of an animal. I am not a biologist by any means. I took biochemistry once, so I'm really not good at this stuff, but if you love biology and you love this stuff, do it for all. Jeez, just do it. Without enzymes, the above reaction is just too slow and does not matter, and you're dead. So with this, I do kind of think this stuff is cool. So in enzymes, there's like this is a little pocket, and then there's these perfect little shapes that can fit right in there, and if they don't fit, they don't work at all. So temporary bonds between an enzyme and a substrate. So this is the substrate right here, this green part, and the enzyme is the orange part. They will polarize the electron density in a CO bond, which allows the neighboring CN bond to be more easily broken. And there's just like this thing coming in, and then reaction, and then products, and a whole bunch of stuff. Application. So that's all. And that is all for Unit 5. And I think this is a great unit, and I think it's really fun, and you will have a lot of fun with the lab tomorrow. So, see you later.